All right, I thought it would be wise to go over some of those trends that we talked about. And I think this year we actually only talked about two trends. It's literally just one, but we need the first trend to talk about the second trend. And those were general attraction. Okay, when I say attraction, I meant attraction between the protons, they're all together in the nucleus, and V electrons, valence electrons. And we had two trends. We had one that went across that way, and then we had the one that went downward. And it was a little bit odd for most of us to see how these trends actually occurred. Because it's a very similar reason, but there's one direction that has variables that the other direction doesn't have. Okay, so it gets a little convoluted here. Okay, and we said that, if you remember, we said that as we went across the periodic table, and what I mean by going across, I mean, let's say we went from 37 rubidium to 38 strontium. That when we make that click from rubidium to strontium, we add a proton and an electron. We also add some neutrons, but we don't care about those. In essence, we added a proton and an electron. Now the caveat here is that we did that at the same shell or energy level. And you really got to think of these atoms, when we're talking about attraction, it's all about the protons. Okay, the protons are centralized and they're non-moving. Okay, it's consolidated positive power in one central location in the middle. The electrons, for the most part, they just go along for the ride. What I mean by that is they have independent movement. They're not in the nucleus, they're around the nucleus. They're not consolidated in charge. Okay, they're spread out. And they kind of do what the attraction-wise, they're at the mercy of the almighty protons in the nucleus. And if I go back again, I'm talking about 30, so I just picked these randomly, 37 to 38, okay, rubidium to strontium. Well, when I'm talking about attraction of those extra valence electrons, what's going to happen here? Well, I think it's important to note that we're in the same shell. In fact, if you label these 1, 2, 3, 4, 5, we're in the 5s. Okay, so this has an electron of a 5s1. This has an electron of a 5s2. So they're in the same geographic location for the most part. But we added a proton for strontium. We added a proton and an electron, but the positive nucleus is even stronger by 1 plus, right? It's plus 38 instead of plus 37. And we also added an electron, and that's cool too. So the nucleus has to attract now 38 electrons, but they're at the same energy level. Okay, we didn't add any extra shells. So in essence, it's almost as if both powers got stronger, the positive power and the positive charge and the negative charge, and that actually makes a stronger attraction. So as we go across, attraction increases. I for increase. And that trend is, for the most part, held up as you go anywhere across the periodic table. I think the easiest point would be to see that we have all the way up here at hydrogen, we have if we do the solar system model, we have an atom that looks like that. And then over here for helium, we have an atom that looks like that. All right, so everything's the same. They both have the first shell only, but this has now, you could almost say, twice the forces acting on those electrons. So attraction goes up. Attraction goes up means it would be harder to remove an electron. It's glued down better by opposites attracting. Now, So hopefully we see increase in attraction as we go across. Going downward has a variable that going across doesn't have. And that's the inner electrons. Now the inner electrons to the valence, they're actually no good. They're actually a hindrance. Because as much as the valence electrons are attracted to the nucleus, the inner electrons are actually repelling from the nucleus. Okay, let's get rid of the math. Believe I have that picture. Let's get rid of the math. Believe I have that picture. Where did my picture go? Help me. Somebody help me. All right, I'm going to have to pause. All right, I found my picture. I don't know why it took so hard to find, but whatever. It took a long time. It was on the desktop. Who would have thought? Anyway, the inner electrons, we were talking about how the inner electrons are actually bad for attraction for the outers, right? The outer electrons are the valence electrons. Okay, so I don't think my marker's on. Let's turn it back on. Let's go to a specialty color of, yellow. So this is a valence electron, and it's attracted to the nucleus. See, it's got attraction. That's plus minus. But unfortunately, it's also being repelled by the inner electrons. So we have this fighting, conflicting forces at play. Whoopsie. Let's get this back up. Looks like that. Okay, so we have these conflicting forces. We have attraction and repulsion. So what does that mean for our periodic table trend? Well, if I get this back together here, I can picture pause. Well, got the table back. What that means is as we go down, we have a variable that is not happening, some kind of accent there, not happening as we go across. As we go across, we're in the same shell. We're not increasing any valence, at least. As we go downward, we are adding another layer to the onion, another energy level, another shell. Those all mean the same thing. So when we do that, we add a lot of inner electrons. So let's do rubidium again. Rubidium has one valence electron. As I go down, cesium only has one valence electron. Now it's true that there are many electrons different. I believe that's 18. There's 18 additional, electrons and protons. 18 additional protons for cesium. That sounds like higher attraction, right? That's kind of what happened here. We went across, attraction went up. But the difference being, rubidium has 36 inner electrons. Cesium has 54 valence electrons. Okay, so we have that conflicting, we have a little bit of a conflict here going on where they're fighting each other for attraction to the nucleus. So just to make sure we understand this whole column, right, they're all going to be S1s. Okay, so this whole column has one valence electron. And the only difference is we're adding inner electrons as we go down. And the repelling force from those added inner electrons, even though we added extra protons, means attraction goes down. So that we have a decrease in attraction as we go down. So we have an increase in attraction this way. We have a decrease in attraction this way as we go downward. Okay, so that was our that was the attraction trend. Now, most books don't even talk about an attraction trend. They just talk about what's coming up next, which was the atomic size or atomic radius. And I like to do this whole attraction trend because that means that you're going to figure out what this is. Why would I do that? Raldius? Okay, so I'm having issues here. Somebody help. I need Cooper back in here. Oh, is it on eraser? Somebody help. Okay, so atomic radius. Okay, you have to push hard, then it makes it look like a little kid with a crayon wrote it, but that's all right. And we also will have a trend that goes this way and that way. Yeah, and this one's very simple. As long as you understood attraction, well, the radius or size is going to be dependent on that said attraction. If you're more attracted to the electrons, right? If the nucleus is more attracted to electrons, well, that means the atoms will get smaller because the added attraction, remember, the electrons are mobile. They can be moved. The added attraction means that I can pull them in if I'm the nucleus. I'm getting them closer in. And what does that mean for the size? It means that the size decreases. I don't know what's happening here. The world is ending here. That is supposed to be a D. And you know what? We're going to say it looks like a D. All right, so as we go across, we're going to have a decrease in size, meaning get smaller. All right, so we have a decrease. Finally got it. Again, why you have to know the whole paragraph there, because as we go across, we're adding protons and electrons at the same energy level. Those forces get stronger. The effective nuclear charge of attraction, effective nuclear charge is increasing. The electrons are pulled in, right? More attraction means we pull the electrons in, and that means the atom gets smaller. As we went downward, okay, if I go down any area, any column, well, that meant that attraction went down. And if attraction goes down, well, that means the electrons aren't held as tightly. And if the electrons aren't held as tightly, that means they have more power to roam around. That means they're held, but they have more energy to move. And then the net result would be the atom gets larger, plumps up in size. So as we go downward, atomic radius increases. Okay, let me do another picture freezer. All right, now we actually have a new periodic table, and this actually is an atomic radius periodic table. It shows the atomic size. And you can see that for the most part, they actually have numbers here of an actual measurement for this. But you can see there's a general consensus that as we go down in any one spot, we increase. You could argue some of these might break the rules, and it's because they actually do. These are generalized trends. They're not absolutes. As we go down one of the columns, we get bigger, increased. And likewise, as we go across one of the rows, we get smaller. Right? Some even looking from hydrogen to helium, right up the top here, we have a 53 and a 31. That's actually a huge percentage drop. It gets much smaller by adding that one proton and one electron. Okay, the effective nuclear charge, which is the charge felt on the valence electrons from the nucleus, really increases as you go across. We're seeing row 2, since we go from a 167, or even row 3, a 190 to a 71, you can really see the distance of size where we get much smaller as we go across. Okay, so that means that this will be the small corner of the table. This will be the large corner of the table. After this, I only have a minute left, but after this we also talked about ion radius. Okay, and if I hit pause one more time, can't do that. I used to teach a ion radius trend, but here are ions. Okay, and you know that these turn positive because for the most part they go backwards to look like a noble gas or be isoelectric. The nonmetals go forward or pick up electrons. They become negative to look like a noble gas. You can see there's some exceptions, especially if the metalloid's down the staircase. But for the most part, it's true on all of these metals and all of the 9 metals that they call nonmetals. The ions, okay, the ions are the gray ones. The ions of positives, they get smaller. And the ions of negatives plump up. And again, it has to do with the proton power in the nucleus. I have 2 seconds and I will say